how'd this go? The home. Not too bad. That's good. This problem? Yes.
Since the cable is the same cable at E, do you have to divide the tension by 2?
No. Since it's the same cable, the force runs equally through the cable.
Okay.
Yep. If it's 450 on one side, it's 450 on the other, right? It's gotta be. Yep. I think it was 450, right? Yeah. Right? So, this problem, it has this funky frame, right? Frame ABCD, and it's got ball and socket joint here, and it's connected by this cable. It's designed like this so it can rotate up, right? There must be something going underneath the equipment or something, right? And it's designed with that cable so it can rotate up out of the way for whatever it's going to interfere with later. And they want to know, based on the tensile force, from whatever it is hanging down off of this thing, right, that's producing a 450 Newton tensile force in this cable, what would be the rotational force acting along that axis? AD, right? I mean, that's what the problem's asking us for. Right? What's the moment of diagonal AD of the force exerted by the frame? In this case, they say, for the VH portion of the cable, right? So I can just get rid of this. So, my question to you is, we're looking for the moment about diagonal AD. What's the equation for the moment? Let's start with that first. R cross F, right? R cross F. So the moment at A is equal to R cross F, right? Where R is where? Where do I take that position vector? Yes, Raj.
AB.
Well, where's the point? I already told you, moment. What's I just realized what I did.
Oh.
Moment is equal to R cross F. I was just like, where would we take that moment?
F.
Is there any place else?
B.
Yes, we could take it either one of those 2 points, right? And the reason why is because once I have the moment of this force with respect to either one of these points, I solve for that moment. So we'll say we're going to do it with respect to A. What do I do with that moment once I find it?
Project onto AD.
We project it on an AD using what?
Dot product.
The dot product, right? So it's a mixed triple product. Good, excellent. That's all you need to know about this whole problem. You don't. R cross F, where R is the position vector. We're going to do it from A. You can do it from B if you want to. I'm not going to do it here from B, but you could. Right? RB with respect to A cross TBH. TBH, right? Again, unit vector, because we need to break that 450 Newton force into its rectangular components. To go from B to H, and yes, it's going to look like that, the arrow, right? The cable's doing this, right? It's in tension. I remove the cable, this cable's going now, I replace it with a force there. It's going to be equal and opposite acting along that line of action of the cable, right? That's the free body diagram. I'm going to find this moment, and I'm going to project it onto that axis. R cross F, right? R. B with respect to F. F is rectangular component. So BH, what do we got? 0.875 minus 0.375, right? Positive I. 0.375 meters I hat. 0.75 meters J hat, right? Up. Plus 0.75 meters J hat. Minus 0.75 meters K hat, right? That's from BH. Find scalar magnitude. This is all the same stuff, right? We just keep doing it over and over again. 1.125. 1.125 meters. And now I can find the rectangular components of that force, right? TBH is equal to the product of the scalar magnitude acting along that cable and a unit vector. right? They gave us the scale of magnitude, it's 450 newtons. Unit vector is 0.375375 plus 0.75j minus 0.75k, right? All over 1.125. Resolve this, and you're gonna get the TVH, 150, 300, and 300, right? 150 newtons I plus 300 newtons J minus 300 newtons K. What do you think? Make sense? Now I find the position vector, RP, with respect to A. With respect to A, what is the position vector from that point to the, from point A to the force? That's it, that's all it is. Positive 0.5 meters up. Great. To project this, right, I've got to dot this with the unit vector, right, along AD. Actually should not write it that way, right? The unit vector along AD. That's that, right? So I got R, I got F. I just need the unit vector along AD. From here to here. 1I, right? 1I, 1 meter. 1 meter I, 0J, 0.75 or negative 0.75 meters, right? Negative 0.75 meters K. Again, find its scalar magnitude along AD. I think it's 1.25, I don't have it. I think this is correct. Somebody can check that for me, I'd appreciate it. 0.75 squared, I think the square root of that. It is, okay. And, so the unit vector, AD, is equal to the 1I, right, minus 0.75, okay, all over 1.25, which is, 0.6 and 0.816. Yeah, 0.816. 0.8I minus 0.6, okay, right? I've got all three. Now I place this into a mixed triple product. MA is equal to 0.8I minus 0.6K. You know what, I'm gonna move this over a little bit, I'll be with respect to A first. B with respect to A is equal to 0.5 meters up, right? I don't wanna write this out, just like this, so people lambda dot R B with respect to A cross T B H, right? 0.8I minus 0.6K, 0.8, 0 minus 0.6. 0.5I, 0.500, right? 150, 300, negative 300. 150, 300, negative 300. I don't need this. I'm going to put it back. 0.5, 150, 0, 300. Take care, Kevin. Have a good weekend. I'll see you in a week from today. All right, we take the cross, right? That minus that, right, which is 0. 0I plus, oh, it says 0. That minus that, right? Which is 0.5 times negative 300. It's 0 minus that, right? So it's 0 minus 0.5 times 300 negative plus this 0.5 times 300 minus 0. What do we got?
150 plus 150.
150, yeah? J
Plus 150.
and plus 150.
Okay.
Okay. I dot I is 0. J dot J is 0, right? 0 times 150. 0.6 times 150, negative 0.6. Negative 0.6 times 150 is equal to negative 90 Newton meters, right? Oops, that's an N. Newton meters. And that's a scale. K dot K is 1, right? Gotta be careful with that. It's acting along an axis. So it's negative 90 Newton meters, right?